Hello again. Now that we've seen the electronic structure, which includes the electron configuration, the orbital diagram, and the quantum numbers, let's actually play with those to try and predict, well, some physical properties as well. And so that's called effective nuclear charge. So I'm going to jump over to the notes. Wrong. There. All right. So we are on this page. So now that we've seen kind of the electronic structure, let's look at the periodic table and some of its predictive tools. So periodic law is when an elements are arranged by atomic number, of course, but their physical and their chemical properties vary periodically, hence the reason it's called the periodic table. And we're going to use something called effective nuclear charge. And so Z stands for the atomic number, and EFF is basically how effective that proton is inside of our nucleus. So it's the amount of pull that an electron feels. It decreases with shielding, and shielding is blocking from outer electrons. And if you're in the same shell, they all have roughly the same effective nuclear charge. And that probably made no sense. So let's go to the whiteboard. All right, effective nuclear Z. All right, so let's think of it this way. If I have one proton in my nucleus, and I have one electron, so I am hydrogen. This little hydrogen, the electron sees all of the proton's charge. Well, helium does too. There's two of, whoops, that's a minus. There's two electrons, but they both see all of the charge. Because they're the same distance away, because they're in the same shell. Wait a second, what if they're in the S's versus the P's versus the D's? Remember, that is just a probability of location. We still have a boundary, okay? That boundary is our shell distance. And so these two electrons have the same boundary distance, and so they are feeling the same amount of pull from the nucleus. Now, this nucleus has two, and this one only has a +1 pull, so this has more pull or positive pull, so it has more effective nuclear charge because there's more pulling in. All right, well, let's go out one. Let's do +3. Well, we still have two, but then the third one has to go out even further. Aha. Yes, I know I have 3. I know I increased and I have 3, but this one is further away. And these two could shield it. That's supposed to say shielding. All right, so at any given moment, to see if that electron was there, it is shielding this electron, so it can't see the whole +3 charge from the nucleus. And so it has less effective nuclear charge. So our first trend is vertical. As you go down, you have less effective nuclear charge, literally because of size. More shells. Horizontally, you're going to increase Z as you go to the right because there's more protons. All right, so on the periodic table, effective nuclear charge increases as you go to the right and as you go up. So the element that has the most effective nuclear charge, guess what? Is helium. Because it's as close as you can get to the nucleus with the maximum amount of protons. So helium is the absolute best element as far as effective nuclear charge is considered. All right, so who has more effective nuclear charge? Carbon versus, let's say, oxygen. Now, the first thing we need to know is what shell they're in. Oh, look, you're in shell 2, and you're in shell 2. All right, so that's not an issue. So we're not looking at a vertical trend. We're looking at a horizontal trend. And so just from our little trick, I know that it increases as you go over. So this one should have the greatest effective nuclear charge. But why? So we're going to look at its protons. So it's a +2. And yes, there's 2 electrons in N equals 1, but there are, carbon is 1, 2 places over. So there's 2 electrons right here. So it actually has, can't really see that. It actually has 4 protons in its nucleus. Oh, look, they're getting shielded though. But oxygens are in the same shell. So I have 6. There's still 2 in the N equals 1, but now there's 1, 2, 3, 4 out there. But again, they're the same distance. Okay, their boundary is still shell 2. So I don't have to worry about the bigger shells, but I do have 6 protons versus 4 protons. So who is pulling in or who's sucking in tighter? It's the oxygen. So that's the horizontal trend. Now, oxygen versus sulfur, on the other hand, okay, now we're tempted to say, whoa, look, oxygen has 6 in its nucleus, where sulfur has 16. And then we have to count shell, below it. So there is a total of 8 and a total of 18. So oxygen has 8 pulling in, okay? So 6 total, but 4 from the second shell. So oxygen has 8 pulling in, sulfur has 18 pulling in. Whoa, this one should have the greater effective nuclear charge because it has more protons. No, 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 no. Are they found in the same shell? No. Oxygen is in shell 2, but sulfur is in shell 3. It's just bigger and it has more shielding. So who has the most effective nuclear charge? It's still the oxygen. So this one is a vertical trend, where this one is a horizontal trend. Which, our little trick works. We are going to, that was not the one I wanted to draw. We are going to increase as you go to the right and as you go to the top for Z, but we need to understand why. Right. Figure this out. Let's talk about size. Or radius, if you will. What will the effective nuclear charge do of, the electrons? Will it pull them in tighter? Will it let them, go out further? What is effective nuclear charge going to do to the overall size? And again, we have a horizontal trend and we have a vertical trend. But the vertical is easy. The vertical trend, you have increased shells. So obviously you get bigger as you go down. You literally just have more shells. But horizontally, you have the same shell. Okay, we're all in the same shell, but you have more protons in your nucleus. So therefore, it has more pull. And if you're pulling, it's going to suck those outer electrons in, and so it's going to be smaller. So the horizontal trend is you get smaller as you go to the right. So this is following effective nuclear charge. So we can also say size increases. Let me see, that's not a good visual representation. Say that differently. You get bigger. Yeah, this will keep them together. You get bigger as you go down and you go over to the left. Okay, but the key is, do you understand why that works? If you're in the same shell, if you're horizontal, it depends on how many protons are in your nucleus. But if you're in different shells, well, it's just how far away you are from the nucleus. All right, so that's going to explain size. Another thing that we're going to talk about, well, you know what? Let's do ions real quick. So what kind of ions are there? There are cations, positive, and there are anions, which are negative. So what if I'm not a neutral element? What if I'm an ion? Well, we're going to do the same thing. So let's look at sodium versus sodium ion. And I have to get a periodic table that's closer. All right, so for my reference sheet, I'm looking at sodium, and sodium is plus 11. So it has 11 protons in its nucleus. Okay, so here's protons. Well, guess what? So does sodium ion. So let's look at electrons. The sodium that's neutral is pulling on 11, I won't put the plus, is pulling on 11 electrons. But this one's only pulling on 10 electrons. So I have 11 pulling on 10 and 11 pulling on 11. Who's going to suck in tighter? This one should be smaller. So cations are usually smaller than their neutral counterparts. And oxygen versus, let's say, O minus 2. The protons are oxygen, okay, it has a total of 8. There's 6 on the outside, but it has a total of 8. And I didn't change the number of protons, but I did change the number of electrons. And this one is also pulling on 8. But this one's pulling on 10 because it's negatively charged. Well, this one is only pulling on 8. You have 8 pulling on 8. This one is 8 pulling on 10. This one is going to be able to pull in tighter, so it is smaller. So anions are usually larger than neutral. All right, so we have a trend for neutrals, we have a trend for positives, and we have a trend for negatives. Let's kind of put it together in an example. We're going to compare, let's say lithium ion. Let's do an argon. Let's do an S2 minus. Let's do an O. And we'll do a neon. All right. If I had to put these in an order, now if you remember this is ballpark, but it's a pretty good guesstimate. All right, first of all, I'm going to see what shell they're in. Okay, and so lithium is in shell 2. Okay, so lithium is in shell 2. Well, guess what? Wow. This is also in 2, but I'm losing that outermost electron. So it was like this. It has 2 in the n equals 1, and it had 1 in the n equals 2, but this is lost. Okay, in order to become ionic, that has been lost. So lithium is now back down to 1 in essence. So I started as 2, but because I'm positive, I really am in shell 1. All my electrons are in shell 1. Argon is shell 3. Sulfur is shell 3. All right, and then let's look. Sulfur started in shell 3, but to become negative, it had to gain 2 electrons, but it's still in shell 3. Oxygen is in shell 2, and neon is in shell 2. So right now, I know that my largest has to either be argon or sulfur. Or I guess we can start with the smallest, it doesn't matter. All right, so argon, now we're going to do protons. Argon has 18 pulling in. Sulfur has 16. And we'll just keep going since I'm looking at it. This one has 8. Neon has 10. Lithium has 11. All right, so I'm only looking at these 2. Those are both in shell 3. Well, this one is 18 pulling on 18, and this one is 16 pulling on 18, which is the number of electrons. Oh, well, I think 18 pulling on 18 is going to be able to suck in or make smaller. So this one is the biggest. This is the second biggest. And now I'm to shell 2. All right, so let's take a look at shell 2. I've got this one, and this one, because remember that one has dropped down to shell 1. So lithium has 11 pulling on 11. Lithium ion actually is 11 pulling on 10, but it's clear down in N equals 1. And oxygen has 8 pulling on 8, and neon has 10 pulling on 10. So who is pulling tighter? Who's pulling tighter? And so I'm seeing right here. So lithium has 10 protons pulling on. See, you guys need to be here. I'm talking about sodium, not lithium. Sodium is 11. Lithium is only 3. You know, I usually don't mess up this much. It must be just something special for you guys. There, that looks better. So 11 was actually sodium, not lithium. All right, so this one has 3, and it only has 2 electrons now. All right, so I have 3 pulling on 3. I have 8 pulling on 8, and I have 10 pulling on 10. Well, 10 is definitely more, pull in the center. So this one of those 3 is the smallest. The second, and then the third. And then the absolute smallest is this lithium because it's clear down in N equals 1. Now, if I was to go look at the actual numbers, there might be some variations here and there, but this is a pretty good check. So depends on if you want to go larger to bigger, larger to smaller, or vice versa. But the lithium ion is smaller than the lithium, which is smaller than the oxygen, which is smaller than the neon, which is smaller than the argon, which is smaller than the sulfide. And that's how you would figure out a trend. So remember, horizontal and vertical both have different explanations. All right, that is effective nuclear charge and how it affects size. Until next time, jolly out.